All right, so this session is quite a bit longer and going into detail on membrane filtration. So Matt, if you just want to stop me when we're ready for break time, just speak up and we'll cut it there. So with that, we're going to shift gears here to membrane filtration. What is membrane filtration? It utilizes an engineered membrane barrier that allows water to pass but removes contaminants. Unlike what we've just talked about, it achieves particle separation purely by physical removal. So think of a strainer. Basically, it does this by size exclusion. So the pore space, as water passes through the membrane, the pore space is small enough to prevent the particulates from passing through it, just like a strainer. It does not work on the particle attachment concept with the media filter. And also, to push this water through such a small pore space, it does require a driving force to do that. EPA's membrane filtration guidance manual says that in order to be defined as a membrane filter, it needs to reject particles that are larger than 1 micron. Okay, so why membrane filtration versus our conventional filtration? Well, a number of years ago, with the surface water treatment rules getting more and more strict, the membrane filters became a dependable way with certain water qualities to meet the stringent turbidity and particulate removal requirements. With LT2, that's the regulation that's all about reducing crypto. There was a lot of membrane plants put in for that purpose. Not so much in Michigan, but nationally. Also cost, they can have quite a small footprint compared to a conventional plant. And those costs have been coming down as there's more manufacturers, more competition, and the technology has just improved over the years. There is some flexibility and simplicity, small footprint, as I said, and fewer chemicals. All right, so just a little bit of background in Michigan. Here's just a list of the different communities that use membrane filtration. We also have a number of non-community systems that have them as well. I think all of those are located in the UP. Bay Area, that serves Bay City area, is our largest at 17 MGD, and City of Marquette, where I'm located, was the first in the state in 97. And they are located, if you're familiar with your Michigan geography, they're located on all the different Great Lakes, as well as the St. Clair River. So we're seeing them all over in Michigan. Also, we just talked about direct filtration. In Michigan, most of our membrane plants, almost all of them, are direct filtration, meaning they take raw water and they pump it right to the membranes. There's no need to coagulate or flocculate the water with membrane filtration. It's just raw water goes right to the membranes. We do have a couple in the state that do some pre-treatment, and they do that just to get better performance out of their membranes. Okay, so these next 2 slides, for those of you that might be taking exams, this is probably a good thing to be aware of. I've seen these on exam questions before, talking about basically the classification of the different types of membranes, and they're essentially classified by pore size. So you can see up here is the scale. It's like a logarithmic scale for in microns. And you can see RO being the smallest, then nanofiltration, ultrafiltration, and microfiltration. And what is important to point out here, look at the size range of bacteria, algae, cysts, that would be your cryptosporidium, clays and silts, that's a common part of turbidity, and viruses. And look how those sizes compare to these membranes. And so our cryptocysts are over here, and all of these pore sizes are smaller, except maybe the high end of microfiltration. So again, this just shows, as you could imagine, the smaller the pore size or the tighter the membrane, the higher operating pressure will be required. So RO that has the smallest pore size requires the highest driving pressure to essentially push that water through. Also mention these top two, micro and ultra, those are used primarily for surface water treatment, whereas nano and reverse osmosis are more commonly used for removal of organics and dissolved materials like hardness, nitrate, metals, PFAS, that type of thing. And then also these tend to have reject water. So, you know, say if 100 gallons was introduced to those filters, maybe only, you know, 50 gallons goes through it. And then that reject water is then sent to another membrane. And so that's different. Whereas, and I'll show some examples of that. Whereas micro and ultra filtration are in a dead end configuration, and basically all the water goes through. I will point out this entire presentation is going to focus on micro and ultra filtration because this is more of a surface water and groundwater under direct influence course. But we'll talk a little bit about these. Okay, so in the world of surface water treatment, by far the most common are these hollow tube membranes that are pressure driven or vacuum driven. You know, they're submerged in water and a vacuum is applied. And hollow tube outside to in is, again, by far the most common. I'm not sure we have any in Michigan that are hollow tube inside out. That seems like it was kind of an original technology, and I think that the industry kind of figured out that the outside in was a better, more efficient way to do it. There's also spiral wound, that is going to be your RO and nano, and cartridge filters. So again, we're going to focus mostly on this first one because that's what's most common. This is kind of an older figure from the EPA guidance manual, but you can see this one here is the more common. You've got your feed water that comes into this pressurized module, and then you've got your membrane fibers in here, and the water must go through the outside wall of, think of this as a straw, and it goes through the outside wall of the straw through the pore spaces. And then once it gets to the inside of the straw, it's allowed to come out both the top and bottom. That's the outside in. This is the common one. Then there's just the opposite of that flow direction, inside out. This is kind of the obsolete type. And I'm going to talk, if you're not familiar with membrane plants, they can be difficult to visualize because everything's kind of in a black box. You can't really see. But this is the size of one of those individual fibers. And you can see if you had a dime, you can get dozens of them just on a dime. They're tiny and they're really flexible, you know, kind of like almost like a wet noodle. And then if here they are packed in, and if you zoom way in, this is the sidewall of the straw. And so water would come from the outside. It would work its way through that engineered membrane, and then the finished water is on the inside of the wall. And that's how the filtration happens. And again, it's an engineered membrane, so it's highly uniform, and it's capable of very high and absolute removal of a targeted particle size, just as long as it maintains its integrity. And EPA says that it's well documented that if you have good integrity with your membranes, you should consistently be able to achieve less than or equal to 0.05 NTU. All right, so I kind of described this already, but so some of the terminology, these little individual fibers, those are called fibers. When they're all packed inside this pressurized container, that's called the module. And so again, the water comes in on the outside of these, it goes through the sidewall, and then the finished water comes out the center of these fibers. And the end of the module, they call this the potted end. This is like a resin, and that water comes through the modules out that potted end to the finished water area. And you'll notice these have O-rings on them here. So the only thing that separates the raw water from the finished water here are these two O-rings. So the O-rings are a very critical part, and when we do have failures with these membranes, a lot of times that's the culprit, is a bad O-ring, or it got rolled incorrectly when it was installed. Okay. And as I said, what I just showed was a pressurized, this would be a pressure driven. So you'd have a pump on the upstream side pumping up the pressure to force the water from the outside of the fiber to the inside. The other configuration that is out there is these submerged vacuum driven types. And you can see here, you have this kind of the same thing, but there's not the pressurized vessel around it. So what we have here is these are just suspended in raw water. And then there's a pump that creates a vacuum that pulls up from the inside of all of these fibers. And so it's basically sucking it through that way. And so here's a couple just different configuration. The ones on the left here are cassette style, and then these are just suspended in the water. And you can kind of see right here. The one difference in the operation of these submerged types versus the pressure-driven ones is you do get solids that will settle in here, as you can imagine, because this is raw water. Now, you're not adding a coagulant or anything, but you will get settling over time. And so operators will have to clean out those basins periodically. Okay. I mentioned we are not going to focus a whole lot on nanofiltration or RO, reverse osmosis, but this is what that type of membrane looks like. And again, this application would be more for something special like nitrate removal, PFAS removal. Sometimes you'll see it for softening. And so it's so small, it can remove your hardness molecules. So the way it works is you have a sheet of your actual membrane right here, and then you'll have another sheet of membrane, and then in between you have these spacers, and then that all gets rolled up, and so the feed water gets pumped in at a high pressure, because these are really tight membranes. And then the only way for that water to get out is to squeeze its way through the face of this sheet where it can get to the other side. And that's where the permeate collection is. That would be the clean water. And so that's how these ones work. And then the last type of membrane I'll bring up just to complete the classification, I guess, is the cartridge filter. This is not really something we're going to use on a community or municipal scale, but this is something you might have in your refrigerator. But you can see the water comes in, and just to increase the surface area, they kind of pleat. It's a pleated fold that goes along here, and the water just works its way through that. And these are common, like I said, in refrigerators. I actually have one of these for camping. You have your dirty water here and just flows by gravity. It's got one of those cartridge filters there, and then you got your clean water here. All right, so few comments on membrane material selection, and this is something that is done in a design phase, so it's not something operators necessarily need to worry about on a day-to-day basis, but it's just good to know, the basis for the equipment that you have. The material of the membrane itself should be matched with the feed water characteristics, so what you have in your source water, and it needs to be resistant to any treatment chemicals that you're using. A lot of times in Michigan, we need to use a pre-oxidant to keep zebra mussels out of our intakes. So we have to have something that's resistant to those chemicals. And then, as I will talk about in more detail later, these membranes need to be cleaned periodically with chemicals, and you have to have a material that is going to be resistant to those cleaning chemicals. So here's just a few different things: pH, temperature, oxidants. Those are different things that need to be considered when selecting the best material for the membranes. The ones I've permitted in the last few years, these two organic polymers listed below tend to be the most common. That polyvinylidene difluoride, I think is how you pronounce it, seems to be a common one. Okay, again, for those of you that might be taking exams, as you might imagine, membrane filtration comes with its entire own vocabulary, and the people that signed up for this class should have gotten, if not, we'll get it out to you, but I pulled a PDF document of the membrane filtration guidance manual glossary out of EPA's manual. And so there's several pages of terms with definitions. For your convenience, I've pulled out the most critical, important ones. So I'm not going to go through all these right now, but most of these will be covered in subsequent slides. But, a little hint to those of you taking exams, these terms I would know the definitions of, and that glossary will provide the definitions. These are the key ones that, any membrane filtration operator ought to know. Okay, so now again, we're going to shift back to our micro and ultra filtration specifically for surface water, and I'm going to just describe a basic. Every plant's designed a little bit different. This is just one example, but these are some basic system components that you're going to see in most, if not all, membrane plants. All right, so first you're going to have some type of a feed pump. You can think of that as your raw water pump. That's going to pump the water to the membrane module. Almost always it's going to go through a strainer first. The strainer is not going to be nearly as small size as the membranes, but it's there just to protect the membranes. It's keeping, you might have fragments of zebra mussel shells. You might have some chunks of weeds, different types of stuff like that we want to keep off of the membranes to protect them. And that's what the strainer is there for. Then you have your membrane. You're going to hear these called racks, arrays, filter units. EPA has adopted the term filter unit because there's these different proprietary terms. So that's what I'm going to, but basically it's a set of modules that are all similarly piped in, and most plants will have multiple, at least 2, 3, 4 of these racks, arrays, filter units, whatever you want to call it. This is where the filtering happens. You're going to have a backwash pump. You're going to have a CIP, that's clean in place system. So you see where cleaning chemicals are introduced. So there's a whole separate room where you have all your chemical feed, and then that would get piped in for when cleaning is needed. Compressed air system is a critical component for all of these. So you see you have air scour here, that's going to come from the compressors. Control system, piping. You're going to have instrumentation. So you're going to have pressure gauges, turbidimeters, and other water quality monitoring. There may be some safety or equipment protection instruments. Then other appurtenances, valves, actuators, meters, that type of stuff, of course. All right, this is another one that's important. How the operation cycle of a membrane filter plant is a little bit different than a conventional plant. So this is, again, every manufacturer and every application and model and everything's going to run and be set up a little bit differently. But this is an example of a common modes of operation. Filtration, backwash. Sometimes that backwash has compressed air introduced. They call that an air scrub. So it kind of enhances the backwash. Then there may be a chemically enhanced backwash. So it's the same thing as a backwash, except maybe they introduce chlorinated water. Then much less frequently, they would do a chemical clean in place. Usually that's a manually initiated activity, whereas the rest of them tend to be kind of an automated thing. And that chemical clean in place, we'll talk about it more later, but that's to clean the membranes to get a good clean to kind of restore the performance. And then another part, very critical part of operation is integrity verification. And by that, basically, we're trying to identify if there's any tears or holes or breaks in that membrane. So I would point out that these systems are operationally complex, requiring simultaneous monitoring and control of many inputs and outputs. So most of them are based on a PLC with a SCADA interface, and the complexity and the timing of all the valve sequencing and everything makes it pretty impractical to operate these manually. So they are designed to run in an automated fashion. There are probably ways to override manually all these things, but typical operation is done automatically. So because of that, we get a lot of questions about do they, can they run without an operator? Can we just let them go and do their thing? And in Michigan, we have not allowed that. And so here are a few different reasons why operators are important. Their role is important even at these highly automated plants. As I mentioned, the integrity of those membranes is absolutely critical. We really only have one barrier between the raw water and the finished water, and it's that thin little membrane. And so on a daily basis, we need to do a test, the DIT, direct integrity test, and operators need to verify that that test passes each day. Similarly, we also have turbidimeters. online turbidimeters for each of these units, and the operator needs to verify on a daily basis what those turbidity trends are. One of the more challenging parts of a membrane plants, particularly in the winter time, is ensuring you're able to maintain your production. What happens is that cold water gets, you lose capacity. As you might imagine, with higher viscosity water, when it's cold, you can't push as much through the membranes as you can with the warm water. So wintertime production can be challenging. Of course, there's the usual data collection an operator would need to do, maintenance of equipment, and there's specific equipment with membrane filtration, preparing MORs, verifying your disinfection requirements, your CT, scheduling and initiating your clean in place, ordering, receiving chemicals, and collecting your samples. So still plenty for the operator to do even at the automated system. And so I mentioned before, each plant is designed and operated a little bit differently, but here's an example of what an operational cycle might look like. So the unit might filter for only 15 to 60 minutes and then backwash. Compare that to a conventional filter. They might go 200, sometimes even 300 hours before they need to be backwashed. These do short cycles, then they backwash with or without air. Each day it needs to run a direct integrity test to make sure there aren't any breaches in it. And just to clarify, that means every day of operation. That doesn't mean 24 hours of operation, because if you have a small plant that only operates 6 hours a day, that might be four days, if my math is right, before you would do a test if you did it every 24 hours of operation. So the point is, the requirement is to do that every day your plant is operating. Maybe once a week, perform a chemically enhanced backwash. So that's just a normal backwash, but you might have a high chlorine concentration with the water. And then maybe 1 to 8 times a year, you do a chemical clean in place. And these units usually have a HMI, that's a human machine interface that operators can use to monitor and schedule these different activities. And I'm just going to do a quick time check here. Okay, I think I'm doing good. All right. So backwashing. From previous presentations and perhaps from your operator experience, you're familiar with the backwashing of a conventional filter, but the backwashing of these is a little bit different. In this diagram here, it shows the backwash flow direction. Of course, during normal operation, we would have this outside in configuration. So these arrows would actually be reversed during normal filtering. And so water would come through, it'd work its way through this wall of the fiber, it would get into the middle, and then it would go out with the finished water. And all the stuff we do not want in the finished water would be rejected and on the outside of the fiber. So as you can imagine, that gets dirty and also kind of plugs up your open spaces after a while. And so what they do, it's pretty simple. They just reverse the flow. So now you have finished water that is going through the center, pushing out. And then a lot of times they'll also on the outside of the fiber introduce compressed air. And so you get air bubbles that kind of agitate. And so between the reversal of the water plus the agitation with the air, it does a pretty good job of clearing all that, those particulates off, and then, it just goes off to waste. And then, as I said, some of these systems are set up to do a chemically enhanced backwash. So they might do the same thing, but with a highly chlorinated water. And sometimes that is a longer duration where it might have a soak step in there just to help out. So, all right. And I guess I should also introduce the concept of TMP, that's transmembrane pressure. So you're going to have some pressure loss. You measure the pressure out here and the pressure in here when you're filtering, you're going to have some pressure loss as it works its way through here. And as you can imagine, as this gets dirtier and dirtier and plugs up more and more, you're going to have a higher transmembrane pressure. So that the difference between here and here is going to increase with time. When you do this backwash, that's going to help restore and bring your transmembrane pressure back where you want it, but it's not going to take it all the way back to original. In order to do that, we do a clean in place. And this is the one I said that is a lot less frequent. But depending on your source water, you can and will in time foul the membranes. So if you imagine, you know, an extreme example, if you imagine like water that's really high in iron or really high in hardness, and that going through these membranes over a long period of time could start to foul. You could get that iron buildup, like, you know, embedded right in the sidewall of that fiber. So organics will also do that. So a CIP is necessary to remove those accumulated materials that you're not able to get through your normal backwash process or chemically enhanced backwash process. So in order to usually when a membrane plant is designed, the manufacturer will look at the source water and they will suggest a clean in place chemical based on, you know, what's foulants are potentially in the source water, what your membrane and seal materials are, and then you also have to consider handling and disposal, because some of these chemicals are acids or bases, so they need to be handled and disposed properly. And as I said, the frequency to do this will very much vary on your source water and other factors. So it's going to depend. And again, the goal of a clean in place is to return the membrane's transmembrane pressure back to the baseline. So here is a graph that helps visualize that. On the top, this dotted line is an example of a system that has a clean in place regime that is not very effective and not doing a good job. So here is this line right here is the baseline original transmembrane pressure, meaning if you have a new clean membrane, this is all the, you know, difference in pressure you have between the feed water and the water, the clean water coming out. As that membrane starts to get dirty, it's gonna get that transmembrane pressure will build up. Then they do a clean in place and it improves. But with this bad one, notice it didn't improve all the way down to the original. It only got to here. So there was sort of some permanent fouling that occurred there. And then they go down their next cycle until their next CIP. And they do their CIP and they're even further from the original. And you can see in time, you've now permanently fouled that membrane, and it's expensive to replace all those membranes. So as an operator and a designer, you want to design and operate this thing to get the most life out of those membranes as possible. So this solid line is an example where you have a good CIP regime. It builds up, you do the CIP, you bring it right back down to original. And, you know, same thing happens there. So that is that's what we're trying to do with the clean in place. All right, a few more comments on the design of a clean in place system. So, you know, if you go into a membrane plant and go into the room with the CIP, it looks a lot like a typical chemical feed room. You're going to have chemical barrels, you're going to have a day tank, you're going to have a chemical feed pump, but you're going to have a few other things you don't normally see. You're going to have a water softener and usually a water heater and a big hot water tank, storage tank. And as you might imagine, just like when you wash clothes or whatever, it's more effective to use warm water. And same thing with these membranes. If you get hot water that's softened, why do we want it softened? Because we're trying to remove foulants, and those hardness molecules could you know, foul. So we want to have hot softened water with our CIP chemical mixed in, and then that will be recirculated and soaked. The membranes will be soaked and, you know, recirculated to try to get those any foulants that have kind of become embedded in the wall of that membrane. And then, as I said, some of these chemicals are strong acids and bases or surfactants, so they have to be neutralized and then properly disposed, usually to the sanitary sewer. And then after that, of course, they need to be flushed with potable water or raw water and rinsed before you return to service. All right, so with this slide, I want to talk about an important, since we just talked about CIP. As you might imagine, now we have a potential serious cross connection because we have, I just mentioned, strong acids and bases, and those lines are directly connected to these membranes because this is all done kind of in an automated fashion. And so it's a little difficult to read here, but I'll walk you through it. So this bold line is your normal water coming in, comes into membrane rack B and rack A. And so normally the water goes through here, comes out, and then here's your filtered water. But you'll see we also have a CIP, clean in place chemical solution line that comes in and it ties in here. So now right here, we have a direct connection between potentially nasty chemicals and our water. And so in order to prevent that, we need to have backflow prevention in place. And the most common way to do it is by use of what we call a block and bleed valve. So, or double block and bleed valve, I should say. And so you can, what it is basically two isolation valves in series with a drain valve in between. So your feed water normally coming in, this drain valve would be closed and these would be open. And then your CIP line that has your chemicals in it, which ties in right here, normally, because again, you only do your CIP infrequently throughout the year, this would be closed, this would be closed, and this would be open. And so the purpose is if this first isolation valve failed for some reason, because it's a mechanical piece of equipment and it will fail eventually, rather than those cleaning chemicals now being right up against this valve, which could also fail, it would just drain out through this open drain valve. And so that should normally be kept open. And if operators notice that it's dripping chemicals or dripping water from this side, then they would know one of those valves needs to be replaced. Now, once you do your once you do switch modes and you're actually running your CIP, let's say for rack A, you're gonna close these two valves, open the drain valve. And then the CIP, you're gonna close the drain and open these. So now your chemical is gonna come through, be introduced here. It's gonna wanna go there and it's gonna wanna go here, but there'll be a closed valve. If this were to fail, this should just drain out. But imagine if we just had a single valve here. If we had a single valve and it failed, that cleaning acid or base could go through that leaky valve and then it would go right on to your next membrane. And these membranes are not designed to remove acids and bases. They're designed to remove turbidity. So that acid and base would go right through, right to your finished water. I encourage, if you are an operator of a membrane plant, to go back to your plant and find these. There's likely going to be multiple ones, and every one is designed a little bit differently, but here's a real world example, and you can see if you didn't know better, you might be asking, why in the heck would you have two isolation valves right in a row? Makes no sense. You just need one, but you've got that drain. And so here's just an example of one of those. Okay, just doing a time check here. Where are we at? 10 o'clock. Okay.
I think we're about due for a break, Mike. Matt?
Okay. Yeah, that's a good spot for me.
All right, Martin, how long do you want to take for this break?
We will take about 10 minutes.
Okay. We'll go ahead and bring the clock up. Right. All right, so you should see the clock up there on your screen. We're going to go ahead and start that. And we will see you back at 10:10. All right, 10 minutes is up. You're all coming back in, and we're going to go ahead and start out with a poll question. So get that up. All right, you should see a poll question that has popped up on your screen. What step in the conventional treatment process is eliminated in the direct filtration process? So remember, if you need continuing ed credits, you do need to answer this question, and we will share the answer in about a minute or so. So Mike, I did share my screen over yours, so we do not currently see yours, and you will need to reshare your screen again.
All right, very good.
All right, so we're about 80% have responded to this poll. All right, up to 85% on this poll. If you're having some issues with it, feel free to use the Q&A and let me know. And in order to see the poll, your Zoom window does need to be your active screen on your computer. All right, looks like we're stalling out about 85%. So I am going to go ahead and close this poll question and share the responses here. I think you can see these, Mike. We had 29% think coagulation, 24% flocculation, 44% with sedimentation, and 3% with chlorination.
Yeah, so perhaps to alleviate a little confusion, I mentioned that when we say direct filtration in this question, what we're generally meaning is a conventional type filter, so a dual media or a monomedia filter. Although I think what I may have tripped folks up on is I mentioned that membrane filtration can also be a form of direct filtration because you're putting the raw water right on. And in membrane filtration applications, it is true you would not have coagulation and flocculation, but in where we have media filters, you absolutely would have the coagulation and flocculation. So sorry if that was confusing, but I think most folks probably gathered that. So Matt, I think I'm pretty good on time here. I was just going to add a couple comments on questions I saw in here. And Martin, thanks. You provided some answers, and I think you pretty much covered it. But one of the questions we had was, would you see these membrane filtration systems in lower populated communities? And as Martin said, it's kind of a spectrum, but I think the small. I think it's more if you have a small community that needs to do surface water treatment, membrane seems to be the way to go. It's a lower capital cost. And the last few small communities that have done surface water in Michigan both put membrane plants in. But they can also be used. And I think the reason for that, for a small community to build a conventional plant with such a massive footprint, it's usually just not viable. So good question there. And then, are the modules reusable? So we got to be careful with the terminology here. The modules are basically that cylindrical pressurized container or vessel. Those are absolutely reusable. But inside of that, you have your, the cluster of fibers, and those slide out of the container. And those, as Martin indicated, do have a lifespan. They will eventually either get fouled or sometimes they just become brittle and they'll have so many breaks in them that it's just time to be replaced. So the fibers, the membrane, the actual membranes that do the filtering, those are, I would say 10 years is probably a good lifespan that you would get out of those. The rest of the components are, stay in place. So hopefully that answers the question. If not, add some clarification in there. But with that, I will jump back into the presentation here.
All right, so Mike, I just want to remind we need to see your screen. And then we did have one question in the hopper. So what was the correct answer to the second poll?
I would say, because the intent behind it was for a conventional type filter, the correct answer would have been sedimentation. That would be the step that would be missing.
Thank you.
Awesome. Thanks, Mike.
Very good. All right, hopefully I'm sharing the right screen.
Yep, you're in presentation mode. Take it away.
All right, I just got to get my speaker note thing going here. So give me 1 second. Oh, darn it. Show presenter view. Okay, I'm still looking good to you guys?
Yes, you are.
All right. All right, so well, coming back from the break, and it's good because the next topic is arguably the most important part of membrane filtration. So to take one giant step backwards, visualize a conventional water treatment plant. You have water coming into the plant, you add a coagulant, you do rapid mix, you have flocculation, you have a settling basin. And in that settling basin, you are removing the majority of your turbidity there. And then from there, it goes on to filters and sort of gets polished, we call it. It's kind of that last bit of turbidity is removed. And then it's disinfected. And so you have all of that turbidity removal and that settling happening in that settling basin. So we refer to that as multi-barriers. You got the coagulant, you have the settling, you have the filtration. So it's like 3 barriers right there. Whereas membrane filtration, the biggest disadvantage, I would say, is you are putting all your eggs in one basket. You are very much relying on the integrity of these little flimsy fibers. And so for that, so you really just have one barrier. All that is separating the finished water that people are going to drink from the raw water that we presume has contaminants in it is this thin little membrane. So for that reason, the state and federal requirements are you must perform a direct integrity test each day. And so, and the goal of that is to detect any holes or tears or breaches in the integrity of the membrane. And the most common test to do that is the pressure decay test. So if you're familiar with how to pressure test a water main, it's very, very similar. You're configuring and manipulating the valves to pressurize these fibers, and you isolate and pressurize, and then you just monitor the pressure for a duration of time. And so if you look at this little graphic here, would be in direct integrity or be in pressure decay test mode here. And in this instance, we have a leak. You can see the bubbles coming out. So air is introduced to the inside of that tube, and that pressure is held. And if there is a hole in it, as you can imagine, that pressure will decrease. And just like with a water main pressure test, with a membrane pressure decay test, there is also an allowable amount of leakage. We can tolerate some, but as an operator, you must be aware of what that limit is. And there's no magic regulatory number. That is a manufacturer model specific value. And so a fundamental part, and this is something that Eagle will ask during sanitary surveys when we're out at a membrane plant, are you aware of what we call it your upper control limit? So that's basically the pass or fail value for your direct integrity test. You have to know what that is. And if you don't, you contact the manufacturer and they'll be able to provide that for you. And so also there's a minimum test pressure that's determined also by the manufacturer, but that's a good thing to be aware of, just in case there was some type of problem with bringing the thing up to pressure. And these systems, these membranes go through, we call it a challenge test. That's all done in the factory before you even get the membranes, but they have to be they have to be designed such that they would detect a 3 micrometer break. So if it's not able to do that, then that particular model would not likely get approved in any state. And also just note that 3 micrometers, that's not arbitrary. That's about the size of a cryptocyst. So basically they're saying you have to be able to detect a tear that's so small that it would pass a crypto cyst. So as I said, very critical. I want to skip ahead real quick here. Okay, yep. So to get my thoughts organized here. So a couple other comments on the direct integrity test. These systems need to be designed so that they are subjecting all of the various physical components to that pressure decay test. The main thing we're looking at is in this slide, a tear in the sidewall of the fibers. But as I mentioned earlier, there are other failure points. These O-rings. Again, the water is introduced on the outside here, and it goes inside through the sidewall of these fibers and comes out this, the red potted end there. All of that filtration would be bypassed if you had a bad seal here. That raw water would go past the O-ring and right on out. So when we do the direct integrity test, that must also include those O-rings and seals, the potted material. Sometimes if you get a crack, I shouldn't say sometimes, if you got a crack, this is hard. If you were to feel it, it's just it's a cured resin there. So it's a hard surface. You can knock on it. If that were to develop a crack, which I have seen happen, again, you have raw water that would totally bypass. So all of those different components need to be part of that direct integrity test. And that's not something the operator does. That's something that is designed by the manufacturer. And if it's not done that way, those challenge testing would be a failure and they would never get approved to be on the market. Okay. Another thing I want to point out, and I don't know which manufacturer this is, and not all the systems are designed this way, but I've seen these I would call them blocks, distributor blocks, that a lot of these racks are made kind of like in a modular fashion. So you can just add on more of these blocks and more of the modules. You know, say you're gonna upgrade the size of the plant. And so you have this distribution header on the top and bottom that feed these modules. And they're made up of these little blocks that just, you can see right here, there's a line, they just fit together in a modular fashion. So, you know, a big plant, there might be 20 of these that make up the header. In a small plant, there might be 5 that make up the header. But what's interesting about the design, it's nice because it's so compact, but your raw water comes in here, it goes up, and this is a different view, so it'd be coming up through this space right here, and then that's what feeds the modules. And then once it's filtered, the filtered water comes down right here and then comes out. So you actually have your filtered water pipe inside of your raw water pipe, which I don't really particularly like because that's like a common wall. But you'll see where I highlighted in red here, you would have a seal or an O-ring there. And that's another failure point. So if there was, you know, during installation, if that wasn't done correctly, your raw water could get pushed right into your finished water. So the installation of these are very important, and the initial testing is very important to, you know, catch any of those type of failures. So again, this is not something you need to worry about day-to-day operations, but it's important to understand how these work and what those potential failure points are. All right, so again, I want to go back to what I said before. The integrity of these membranes is the most important operational factor here. You know, these type of systems, unlike conventional treatment, it doesn't really matter what's going on with the source water. If you have really high turbidity, as long as you have integrity of your membranes, you're still going to get your you know, your typical low turbidity finished water and good removal rates. All of that is true as long as you have integrity of the membranes. And as I said, so we do that direct test on a daily basis, but that's just once a day. So what happens if right after you do your direct integrity test, you form a tear or a hole, or an O-ring fails or something like that? Well, what we do is, in addition to that, we have another layer of redundancy here. We also have online turbidimeters on each filter unit. And if it's a bad enough breach, then you would see an increase in turbidity, and it would be alarmed and caught that way. So we don't have to wait until the next operating day to determine there was a problem. And so the way I think of this in my simple mind is your indirect integrity monitoring with your turbidimeters. Think of that as like the oil pressure gauge on your displayed on your dashboard. That's, you know, anytime you glance at it, you can see what your oil pressure is doing, but you're relying on an instrument. It's not actually looking at the oil. Whereas a daily direct integrity test would be popping your hood, putting your dipstick down there and actually witnessing what that level of oil is. So the direct integrity test is just that's a true witness of what's going on. And the indirect integrity monitoring, or the turbidity, is kind of a real-time indicator. Okay, and I'll also point out, I mean, these membranes are so small, you could have a failure of a direct integrity test that would not necessarily show up as a spike in turbidity. And so I guess that's one thing to be aware of. And, in terms of what type of finished water turbidity would be of concern for a membrane plant, and this comes from the EPA's membrane filtration guidance manual. If you have a filter unit that is seeing turbidity of greater than or equal to 0.1 and 0.15 NTU, that needs to be removed from service and looked at. That's not a regulatory violation, but that's a sure indicator that something's not right, because again, the way these membranes are designed, they should definitely be able to have better performance than that. So that's an indication of a problem. Now compare that to a conventional filter. You might not take a conventional filter off. I would like to see it below 0.1 for a conventional filter, but some plants are not capable of doing that, and they might not pull it offline at 0.15 NTU. So yes, membrane filter plants are in a sense held to a higher standard. First, with adequate membrane integrity, like I said, the technology is fully capable of consistently being below 0.15. I would say closer to 0.05. And so if you get to that level, it's an indication of a problem. Second, as I described before, the membrane plants, they do not have as many barriers of protection as a conventional plant, such as coagulation and settling and stuff. So for that reason too, it warrants an investigation at a lower turbidity level. All right, so given the number of fibers that you have packed into one of those modules, and then the number of modules you have per filter unit, and then the total number of filter units, a single breach in a module might not be even detected during your direct integrity test, and certainly not with your turbidimeters. However, it can be detected by sonic testing or certain bubble tests or other methods. And so when you're doing it, if there's a failed direct integrity test, what needs to be done is the system needs to be shut down, and you need to do diagnostics on it. And so a lot of the operators at well-run membrane plants that I've talked to, in addition to their direct integrity tests, they also do their own, they call it an integrity verification program. So they will go periodically and they'll do sonic testing, and just it's a glorified stethoscope that they stick on each of these modules. Somebody demonstrated it for me once. You put the earpieces in and it sounds exactly like you would guess. You just hear bubbles. You hear air bubbles in there. That's an indication that you got a breach. And they'll put it in a sonic testing mode, so it'll put air to the membranes, and then you just listen, and if you're hearing bubbling, then that's a problem. And then if you find a problem, then you need to go in and either we say repair. You're basically taking that one little fiber out of service by either inserting a pin, or sometimes with some of them there's a little epoxy that you put in there to plug it off. And also on your monthly operation reports, if you failed a direct integrity test, that's something that needs to be reported, and indicated that it was corrected. All right, so here's an example of that module. I guess you call it a test housing. So you would actually take one of those modules, you valve it off, and you'd actually remove it from the rack, bring it out to your test bench here, and you stick it in this vessel, and then you put an air compressor to it, and you look at that potted end, and if you see air bubbles coming out, then that indicates that that one little fiber, and if you're you know, my age where your eyes are starting to get bad, you're probably going to need some cheaters or something because they're small little holes, but you'll see air bubbles coming out. And then the manufacturers have these special little pins, plastic pins, and you just have to, takes a little eyesight and dexterity, but you just got to put the pin in and then snip it off. And then you have essentially, taken that one little fiber out of service. And so if you have, you know, a abundance of fibers that have pins in them because you've had that many failures, that's an indication your membranes need to be replaced. But there will be failures, and so this is just a way to take, you know, to be able to continue to use these until it's time for replacement. And so this is the pressure driven style. I mentioned earlier we have vacuum style ones that are submerged in water. I'm less familiar with how these work, but here's a photo of one where it is, this I believe is a xenon, if I'm not mistaken, and it's a cassette style. So the membranes are like in this plastic cassette, and here it's in the test chamber. I believe this is where you connect up your compressed air, and then I think you just watch, and same thing, if you have bubbles or something coming up out of the potted end. I think with these, rather than pins, if I'm not mistaken, you just put some resin or something in there to seal it off. So again, going back to, well, these plants are so automated, what are operators needed for? These are the types of things. You need to have a membrane integrity verification program, and to try to keep these keep the integrity maintained as much as possible. Here's another style. This is a small membrane plant, but this would not be a direct integrity test, but this would just be a diagnostic thing. You can see it's a little difficult to tell, but this face or flange right here is actually like a thick, transparent plexiglass. And so you can put this in an air mode, and then just with a flashlight, look in here, and you're looking like, it's hard to see, but there's a header here, because, you know, there's maybe about four or five more of these behind this one. And you just look in there, and if you see air bubbles, that tells you that you got air coming up, and you've got to, so it's like a screening test. So rather than pulling these out and putting them in the test module, you can just take a peek in there, and if you don't see any air, then maybe you don't need to do that. And if you see air, then you know, okay, one of them needs further investigation. So that's just another option that they can do. And so I guess on that sonic testing also, I mentioned the stethoscope. What I've been told by operators is and how they were trained by the manufacturers, is they'll just go through module by module. They'll take the stethoscope, they'll listen here at the top, they'll listen here in the middle, and then they'll listen down on the bottom, and then they just go on down to the next one. It's a bit tedious, but and if they hear bubbling, then, you know, that one is got to come out and identify where the breach is and pin it off. Okay, so kind of winding down here, but membrane filtration versus conventional filtration. I talked a lot about this, but conventional requires careful control of the pre-treatment process and filtration rate. So your coagulation, flocculation, sedimentation, as well as your filtration rate. Whereas membrane filtration, turbidity removal performance is largely independent of pre-treatment conditions, flux rate, and raw water turbidity. So if you're a conventional plant and today or yesterday you had 5 NTU coming in from the lake or wherever you're pulling from, and today all of a sudden you get 50 NTU, that could make for a very challenging day of treatment. Whereas with membrane filtration, if you have that same thing, as long as you have your membrane integrity, you're not going to likely see any change in your finished water turbidity. You may have a reduction in your flux rate or your transmembrane pressure because you're getting, your membranes are getting dirtier. But actually, as those membranes get dirty, sometimes it can actually reduce the amount of turbidity because those pore spaces are effectively even smaller. But you may run into problems with production where you got to backwash more often because things are plugging up. But the point is, as long as you have that integrity, that finished water turbidity removal performance is going to be pretty consistent. So, as I said, the key point with membranes is integrity is critical. So, those membrane pores are smaller than your target pathogens, so removal is consistent and predictable as long as you have the integrity. Okay, note on flux rate. Again, hint to you test takers, flux rate is one of those glossary terms you should be aware of. I would say flux rate for membrane filtration is analogous to your filtration rate for conventional filters. So, and they have kind of a different, the industry has kind of a different unit. I think it's GFD. And I forget exactly, it's gallons something per day, but it's analogous to your filtration rate for conventional filters. But you can just basically think of it as the flow rate per a square foot or whatever of membrane material. So in terms of the filtration rate, theoretically, if you maintain your integrity, you can have an extremely high flux rate or an extremely low flux rate and still get the same turbidity removal performance, theoretically. However, pilot testing in the design phase is recommended to identify what your optimal flux rate would be. And, the advantage of a high flux rate is it increases, your instantaneous production. But as things plug up on the outside walls of those fibers, it will increase downtime associated with backwashing. And so there is kind of a sweet spot, and that optimal flux rate will result in maximum productivity throughout the production day. And there's actually a term for it called critical flux, and that's kind of defined as the point at which a small increase in flux will result in a large decrease in filter runtime. So once you get to that point, you don't want to run it any further. But again, this is not something that operator generally needs to worry about on a daily basis. This is more of a design thing that the manufacturer will recommend for operators. Another key thing to note is your flux rates will decrease with cold water. You're not going to be able to get as much water through. However, from a regulatory standpoint, we are aware of that. And so when we have our membrane plants designed, we say you need to be able to meet your peak day demands with cold water. Now, generally in Michigan, our peak demand days are happening in the summertime when the water is warm, so it's not usually an issue. but not always. We have, we have university communities where, their maximum day demands are when school's in session. And so they may have as much or more demand in the winter than they would have in the summer. So, but that's something to be aware of with the cold water. All right, we are on the home stretch here. Eagle presentation wouldn't be complete without some comments on regulations. So let's talk about how the regulations apply to membranes. So the surface water treatment rules require 3 log or 99.9% removal / inactivation of Giardia and crypto. That is regardless of what technology you use. You have to get, if you're treating surface water, you have to get 99.9% removal / inactivation. So per the long-term 2 surface water treatment rule, membrane filtration plants must meet 3 criteria to be awarded removal credit. Number 1, must meet the definition of membrane filtration. Number 2, has to pass and go through specific model challenge testing. That's all done in the design phase for the manufacturer. And it has to be capable of performing daily direct integrity tests, and have continuous indirect integrity monitoring. That's your online turbidimeters. And then of course you must meet your turbidity limits. So if you meet those conditions, then you get awarded that removal credit. By the way, the definition of membrane filtration, that's way back in the beginning, and that really has to do with what that nominal pore size is. So it's got to be below that 1 micron, I believe, is the number. All right, so basically, if you get, let me skip ahead again real quick. Okay, so basically, if you meet these criteria and you meet your turbidity limits, you get 100% removal credit for crypto and Giardia for membranes. That's an advantage. A conventional treatment plant only gets 2.5 log credit for removal. And the reason is those membranes are, again, if you have that integrity, they are consistent, consistent low turbidity performance. So the research and regulations will credit you with 100% of crypto removal credit that you can get for filtration. I'm going to skip the next slide and go to this one because I didn't have the order right here. But what about viruses? So if you picture way back in that early slide that I had that showed the membrane pore sizes compared to the different viruses, bacteria, cysts, and whatever, the viruses, the pore size of some of the particularly ultrafiltration are small enough to remove viruses. And in fact, they do remove a lot of viruses. And the surface water treatment rules requires a 4 log or 99.99% virus removal / inactivation. But here's the key point. Even though these membranes are small enough to remove viruses, Michigan and no state that I'm aware of have awarded virus removal credit for membranes. And the reason is, even though you can get the removal, those direct integrity test methods are not they're not fine enough or small enough resolution to detect that small of a breach in the membrane. Viruses are very small, and the rule requires you got to be able to detect a 3 micron hole or breach, which is about the size of a cryptocyst. But the viruses are another couple of orders of magnitude smaller than that, and the technology just isn't there to detect that level of a breach. Therefore, even though the removal might be happening, we cannot verify that it is. So for that reason, no credit for virus removal. And so 100% of your virus inactivation must be achieved through disinfection. But that's not that big of a deal because viruses are very sensitive to disinfectants like chlorine. So to get that CT credit for viruses is not very difficult, a small amount of detention time. So I just want to point that out. It's challenge testing. I'm just going to skip that in the interest of time. All right, regulations. What about another part of surface water treatment? We tend to emphasize, rightfully so, we tend to emphasize turbidity removal because that's a acute contaminant that we're dealing with. But another big part of surface water treatment is removing and controlling your organics, because if you have excessive organics in your water and you introduce your disinfectant, then you're going to be forming disinfection byproducts, and there's that whole balancing act. So how do the disinfection byproducts rule apply to membrane plants? Well, micro and ultrafiltration are not small enough pore size to remove those organic chemicals, so they're not really effective at TOC removal. And natural organics may cause issues with disinfection byproducts. So if you have a source water that's high in TOC and the species of organics are the type that form byproducts, membrane filtration may not be a good application. Or you might have to do like the few we do have in Michigan where they pre-treat. They have coagulation, flocculation, settling, and they get a lot of that TOC removal in that step, and then they do the membrane filters. So the federal surface water treatment, or the federal requirements to get TOC removal, that does not apply to membranes, out of a recognition that membranes just don't have that capability. However, those water systems still must meet the MCLs out in the distribution system. So again, we do have a couple of membrane plants in the state that are challenged with disinfection byproducts. They have to perhaps manage their distribution systems more carefully. They might have to do some aeration in their water towers. They may have to be very careful with their dosing of their disinfectant to try to keep that under control. So I am going to stop there. I will point out when I personally got my crash course in membrane filtration, these two resources were invaluable, particularly EPA's membrane filtration guidance manual. That's free online. Just Google it. You can find it. If you're operating membrane plant, it's a great resource. It has appendices that give example integrity verification programs. It talks about necessary operation and maintenance. It talks about the regulatory concepts. AWWA's M53 is another excellent resource. And then I listed a couple others here, but these are great references for membrane. So I'm going to stop there and turn it back over to Matt.